So, good evening, everyone. So, welcome to this live hangout for this course, Fundamentals of Electronic Materials and Devices. So, the idea behind this live session is so that I can answer some of the questions you may have related to the course material. If you actually look at it, we have so far done it around 4 weeks. So, the first 3 weeks were on the materials part, and we just started the devices. So we started with this week we posted week 4 videos, which is for metal semiconductor and PN junctions, and in the remaining 4 weeks as well. So we'll again talk some more about devices. So what we can do is I have some questions related to the course, which I will try and answer. And again, if there are any more questions from your side during this live hangout, you can type it in through the chat window, and I would then be also be able to use that to answer some of the questions. So just going through the questions. So one of the questions by Venkatesh is to actually ask, why do we normally choose different semiconductors for different applications? So why not just use the same material for all the applications? And the reason, of course, is it depends upon what property you're looking at. So primarily, when we look at optical properties, we have something called direct and indirect bandgap semiconductors. So I will just try to have a small illustration to explain the difference between those two. Shall just give us a couple of minutes, we will just set it up. So the question was, why do we use material like, say, gallium arsenide for LEDs, while silicon is used for most other materials? So for optical properties, we need something called a direct bandgap. So we normally represent this by something called an EK diagram, where E is the energy, which is along the y-axis, and K is the wave vector. We normally take the reference to be the top of the valence band. So you remember reading all the assignments, everything is with respect to the top of the valence band. So this is the valence band, just a schematic representation, and this is the top of the valence band, so the 0 point. If the bottom of the conduction band is also at the same value of K, so this is your conduction band. So if these two, the top of the valence band and the bottom of the conduction band is your band gap. If these two lie at the same value of K, we say that this is a direct band gap semiconductor. So gallium arsenide is an example. So for almost all optical applications, it is not so much a necessity. That we will see later when we come to solar cells why. For almost all optical applications, we only need direct bandgap semiconductors. So we would have really liked to use silicon, but the problem is silicon is an indirect bandgap semiconductor. So again, if I were to schematically represent this would be the valence band. For silicon, the bottom of the conduction band is not at the same K as the top of the valence band. So this is an indirect bandgap semiconductor. So silicon works great when you're looking only at electronic properties. Its band gap is 1.1. which means it is fairly stable at room temperature. You can get good conductivity by doping. Silicon also comes from silica, which is a very well or very widely available material. So that is why silicon is used for most electronic applications. But when it comes to optical applications, we need direct bandgap materials. And depending on the bandgap, so whether it is in UV or visible or IR, we have different materials. So the reason why we cannot use the same material is primarily related to the bandgap of the material. Okay, so now hopefully that answered that question. There was also a question about transistors. Transistors we will get to in week 6 of this course. So there we will discuss about transistors in detail. What I would like to say is in this particular course, we will be focused more on MOSFET, so metal oxide semiconductor field effect transistors, simply because they again find a lot of application in integrated circuits, and we will be able to explain the band behavior of MOSFETs using that. So transistors, as I said, we will come to later, and any questions at that time, you can always use the forum to ask it. So there is one question from student Arun who asked which book should be used for optical and MEMS devices. For optical, so for this particular course, I always recommend this book, Electronic Materials and Devices by Kasab, S.O. Kasab. It talks a lot about electronic materials and devices, but also has some more information on solid state physics. It's a very entry level book which is good for this course. There are also books on devices. So Streetman and Banerjee is a very famous electronic devices book that's been around for really long time. There are electronic devices books by SMZ, SZE is the name, that's pronunciation. So he also has a book on MEMS devices, on optical devices. So SMZ is also a very good book which you can use to look at optical devices. So there's another question by Rajesh, which is on doping in LED devices. So LED is nothing but light emitting diodes. So again, this is a light emitting material, which means you basically need a direct bandgap semiconductor. And in LED, what happens is that you inject carriers into the material. So once we go to PN junction, so week 5 of your course, we will talk about PN junction in forward bias and reverse bias and so on. So in forward bias, you have a large current. So we call that we inject the current into the device. And when the electrons and holes recombine, you basically get light out. That's why they call light emitting diodes, because diode is nothing but a PN junction. So you need a direct bandgap semiconductor for that. And typically, since your light is in the visible region, you normally want a semiconductor with bandgap in the visible region. So you dope in LEDs, one to change the bandgap. So this is called color tuning. So whether I want a blue LED or a white, not white, a red LED or a green LED, doping helps you to change the bandgap significantly. So that is one reason for doping. You also use doping to increase the carrier concentration so that more electrons and holes can be pumped in, which means you have more recombination or brighter light. Right? So that's why we typically say that LEDs are really bright sources. There are other engineering aspects to it, but the fundamental physical aspect is that by doping you increase the carrier concentration. So any specific examples? So again, once we come to optoelectronic devices, we will talk about LEDs, and we'll also discuss specific examples of LEDs. At that time, you'll have more information on doping. There's also a lot of physics behind how do we grow these LED materials. So this course we will not be able to go into details about the growth process, but there are a lot of work done on how we grow these LEDs, because that will also affect the performance of these LEDs. So just going on to the next question. So this is actually a very interesting question that's from a student called Jivanandan, who wants to know that after transistors, so after 5 nanometers, what is the next upcoming replacement? So in a way, this is sort of beyond what we do in this course. So in this course, we are more concerned with devices and the materials rather than fabrication. But for anyone who's following the integrated circuit industry, we know that Moore's law says that every 2 years or 2.5 to 3 years, every 18 months, the size of the transistors should be halved, or the number of transistors should be doubled. Currently, I think we are somewhere at 11 nanometers. The next plan is 9, and then 7, and then 5. So really, the question is what will happen beyond 5 nanometers is something that we don't know. It is so there is work going on to sort of figure out, can we keep on shrinking? So at really small sizes, you're going to hit quantum limits. And the biggest issue there is something called quantum tunneling, which says that if I have two nearby wires and the distance between the wires is only a few nanometers, current going in one wire or electrons moving in one wire will essentially tunnel through the other wire. So it's like you're creating an electrical shock while actually you want the two wires to be separate. So that will be one of the physical limits. There are other limits, especially at small distances. Electron transport becomes something known as ballistic conduction, and not the normal conduction that we talk about, conductivity and resistivity and things like that. That will no longer hold when we look at really small sizes. So there are a lot of very challenging physics problems or very challenging fundamental science problems that we need to encounter, that we need to solve for really small sizes. But there are other ways in which people are trying to overcome Moore's law, and one of the ways is by building what are called three-dimensional transistors. So rather than have a transistor on a single plane, so already we have things called FinFETs, so which are 3D transistors. So people are trying to build integrated circuits itself in 3D. So that will sort of enable you to use more space available and then probably have more transistors packing in, so that you can still sort of get the increased power by using more number of transistors. So beyond 5 nanometers, maybe in the next 10 to 15 years, we will have more clarity on what things are, but there are a lot of fundamental challenges that are still out there that need to be solved before we can go beyond 5 nanometers. Okay, so the next question is by Mukul. So he wants to know, why does resistivity depend upon area and not volume? And then he also wants to know a bit about hollow conductors. So I'll answer the first part of the question, and I think that will sort of explain the second part of the question. So let me try to go back to the share screen for this. So let me go to the share screen here, and let me just clear the screen. Just a minute. So normally when we have a current carrying conductor, we basically say that so current is nothing but the flow of electrons. So we define resistivity, rho as nothing but RA by L, or R is equal to rho L by A. I think that is the more standard form that you see. So the L here refers to the direction, the length along the direction of motion of the current. So this is my current carrying conductor, and we say current is flowing from left to right. So this is the direction of flow of current. We also know that by convention, current is taken to move along the positive side, which means electrons flow in the opposite direction. So electrons flow the other way. So L is basically this particular direction. So if I take some start and some end, so L is basically the length of the conductor. A is the cross-sectional area. So in this particular case, if it is a cylinder, A is just pi r square. So A is the cross-sectional area. So that is why we define resistance as rho L over A, or resistivity as R times A over L. So A always refers to the cross-sectional area. And there is a way to derive this. So we consider the number of electrons that are incident. And we say that if these electrons are moving with some velocity, so n times E is nothing but the charge, because n is the number of electrons, E is the charge of an electron, times some velocity. So usually we call this the drift velocity. So n times E times the velocity is nothing but the charge that is moving per unit area. So if you look at the units, n has units of 1 over meter cube, C has units of coulomb, velocity has units meters per second. So this will have units of coulomb per second per meter square. So coulomb per second is ampere, so that is your current. So amperes per meter square, which is your current density. So any VD sort of represents your flow of electrons, and we usually take flow in one particular direction. So that is why we have the cross-sectional area that comes in. So if you have a hollow conductor, your cross-sectional area will now change. It will be the effective region in which your electrons are moving. It will not be the entire cross-sectional area, but it will not change much. In fact, if your area in which the electrons move are less, so if A is small, you will only increase the resistance of the wire. So for most applications, we don't want high resistance. We actually want resistance to be small, which is why we don't ever use hollow conductors unless you're looking at charge transfer across the surface or things like that. So area here always refers to the cross-sectional area. So let me go back to the next question. So again, there is a question. Okay, so again, there is a question by Kannan on the derivation for the density of states. So I thought I will take that. Sure. So again, let me go back to the screen. So this is again by definition. So density of states this is G of E. That's the symbol that we use. So we always define density of states as number of states. So that is some number per unit volume per unit energy. So that by itself is the definition. So per unit volume gives you per meter cube, that is your SI units. Per unit energy gives you joules. So we normally represent density of states as always per meter cube per joule. And usually for typical metal, density of states can be something like 10 power 50 or 10 power 51. Just some really high number. This is G of E. So you can do a whole bunch of conversions. So if you remember your first assignment, there was a question where you had to calculate the density of states for free electron gas metal. So there G of E was 8 pi square root of 2 me by h square whole power 3 by 2 square root of energy. So energy was given and you had to calculate G of E. So the thing was, question also asked you to convert the units to electron volts and to nanometer cube. So you can do that primarily based on knowing the conversion. So I'll just erase the top part. So we say that 1 joule, or another way, instead of joule, I will just say 1 EB is 1.6 10 power minus 19 joule. So that is the definition of electron volts, which implies 1 joule will be 1 over EB, right? And the question says joule inverse, so you take inverse on both sides. So joule inverse is just electron volt inverse, right? So wherever I have joule inverse, if I want to convert it to electron volt inverse, I have to multiply by 1.6 times 10 power minus 19. Similarly, from meter to nanometer, we know that 1 nanometer is 10 power minus 9 meter, which means 1 nanometer cube is 10 power minus 27 meter cube, or 1 meter cube is equal to 10 power 27 nanometer cube, right? So you're just taking the inverse. So then when you do meter per, so then when you take inverse on this, you basically get n power minus 3. So that is why when you convert from per joule per meter cube, you have to multiply by 1.6 for converting joules to electron volts, and 10 power minus 27 from converting from meters to nanometer cube. So that is how you get the final answer in the assignment. But density of states by itself is defined as per volume per unit energy. So let me go back to the main screen. So at this particular point, I will also see if there are any questions posted in the online forum, which I can try to answer. So I see a couple of questions. So one is by Nishant. So he says he's working on wireless power transfer, and gallium nitride is the best material for this. So again, for radioactive technology, that's something that I'm not really worked with. So I'm not particularly sure what application you're looking for. So we know that some materials like silicon carbide, so there is some work on high power transistors. So there are some materials that are used for it. But this particular radioactive technology is something that I'm not familiar with. So Nishant, if you can send me some more information, through email, I can look it up and get back to you. But at present, for wireless power transfer, whatever information you have provided is not sufficient for me to come up with other potential materials. Then the other question from Vikrant is why indirect bandgap semiconductor is preferred for solar cell manufacturing. So we will look at solar cells later when we actually go through the lesson. But there is no particular choice that the material has to be indirect. The reason why people use an indirect bandgap semiconductor is because silicon is the most commonly used material for solar cells, and silicon is an indirect bandgap semiconductor. The reason why people use silicon is twofold. One, integrated circuit technology using silicon is very well developed, so people have been using it for a long time. So the technology is already there. Again, silicon is widely abundant because the starting material silica is sand. So silicon is also widely abundant. But the other question is why silicon is used for solar cells. And the reason is silicon has a band gap of 1.1 eV, which lies in the infrared region. The solar spectrum starts from UV it goes all the way through the visible, and it also extends through the infrared region. So silicon can effectively absorb the sunlight and then create electron and hole carriers, and then these can then be separated and then taken as current through the external circuit, which is basically how your solar cell works. So that is the reason why silicon is used, because its band gap lies in the IR region, so that it can also absorb a lot of the visible light. You can also use gallium arsenide for a solar cell. It's more expensive because gallium arsenide, the material, is more expensive. Its band gap is slightly higher than silicon. So gallium arsenide is 1.4, silicon is 1.1. So its light absorption would be slightly lesser. But when we do solar cells, we will see something called the efficiency of a solar cell. And then we will look at things like open circuit voltage and basically short circuit current. And that also will have a dependence on the band gap. So we can use different materials provided its band gap is sufficient to absorb, or small enough to absorb all of the visible light. But we use primarily silicon simply because silicon technology is very well established and it is very cheap to make cells using silicon. So at this point, let me just see if there are any other questions from the students. I don't see many questions here. So again, those of you who are watching, you have any specific questions that you want to ask, then please do use the forum to post your questions. So one of the things that if you go through the lessons, you'll find that trying to understand the fundamentals of the devices is actually very important, because once you get the basics right, you will also be able to follow a lot of the ongoing research. So the important thing is, for the last 30 or 40 years, most of the work has been done using silicon as the primary material. But now we actually see an explosion of a lot of other materials being used for devices, especially for niche applications. And some of their proper synthesis methods and fabrication methods are different, which means the properties depend a lot more on the synthesis than as compared to silicon, which is actually a single crystal material. So silicon that is used in your wafers are all single crystal, but a lot of the other materials are polycrystalline. And this has an effect on things like the carrier concentration and mobility and so on. So it's actually, in terms of research, it's been a very well researched area, solid state physics, and the work is continuing on, especially with newer and newer applications. So knowing the fundamentals, so things like Fermi energy, things like p-type and n-type doping, what happens when I form a junction between a metal and a semiconductor, or when I form a junction between two semiconductors. Once you understand the physics behind it, you can actually use it to build a lot of devices. So that is what this course primarily tries to cover. It tries to give you the fundamentals behind both the electronic materials part and also some of the fundamentals related to devices like transistors, p-n junctions, optoelectronic devices, and so on, so that you would be able to better understand what the research that is ongoing in this particular area. So Nishant has just sent a couple of messages. So one is the research paper that he will share with me, so I can look at it. So through the NPTEL forum, we had also announced the possibility of internship for those who are toppers for this course. So this is based on both the assignments. You will take best 5 out of 8 assignments, and also based on the final exam. So we want some information on the kind of projects that we've been working on. So without going into too much detail, I'll just tell you briefly about what we are doing and what are the projects that we are working on. So in our group, we are actually interested in something called printed electronics. So the idea is we use conventional printing technology in order to make devices for very specific applications. So this could be something like a pressure sensor or a temperature sensor. It could be a wireless antenna that you use for GPS or for radio or Bluetooth or things like that. So we do a lot of work on developing materials for printing, and we also work on the device aspects. So some of the materials that we are working are primarily metal oxides, so things like zinc oxide, nickel oxide, copper oxide. These are either N-type or P-type depending upon the synthesis procedure and doping concentrations and so on. We also do some work on metallic nanowires, primarily as transparent conducting transparent conductors, not transparent conducting oxides. So as transparent conductors, metals have very high conductivity that we saw at the beginning of the course. But the same metal, if I take in the form of a nanowire, its conductivity is still very good, but the layer also becomes transparent. So we are working on developing some transparent antennas using these nanowires. We try to mix them with polymers and make blends and so on. So these are some of the areas that we are working on. So the specific topic will again depend upon the background of the particular person who is coming. So we do have some ideas for making, trying to integrate these into very simple devices. So anyone with an electronics or an electrical background who has some knowledge about, programming something with say an Arduino board or something, that would be very useful for us, because then we can try and use the material in order to, come up with some sort of devices. So the specifics of the project we will know more once we have the particular person chosen, and then depending on their interest and background, we can tailor it to their specific needs. So apart from that, I don't have much information on the project at this particular stage. So again, if you guys have any questions, please do use the online chat. So I've gone through all of the questions that are here. So then those which are relevant to the course, I've been able to answer. So some of the questions on devices, for now it will not be very clear. But once we are done with the device part, we could even have another live session sometime in April. So we could again look at some of the questions related to devices and then try to answer those. So if there's not any more questions, okay, so just one more question. So there's a question from Aditya. Can you elaborate more on electron affinity? So again, if you go back to the band picture, so let me see if I can get the screen sharing thing to work again. Okay, so let me then just quickly erase the screen.
I'll take up this.
Okay. So if you look at the band picture of a semiconductor, so again this is your energy axis. So this would be your valence band. So this is a semiconductor, which means there is a band gap. This is valence band. This is a conduction band, and we say this is band gap. And this picture is true whether it's direct or indirect, because there is no k axis. We're only looking at energy axis in the y direction. So the valence band is always full. The conduction band is empty. This is at 0 Kelvin. So Fermi level, we usually always put somewhere in the middle. The top of the conduction band is called the vacuum level, because we say that beyond that, the electron can primarily go out of the solid and it is free to move. So in this scenario, we define electron affinity as the distance from the bottom of the conduction band to the vacuum level. We call it chi. And we say that chi is the energy to remove a single electron from the particular material. So it's also related to something else called the work function. So phi. So work function is what you would measure through an experiment like say the photoelectric effect, where you shine light of some frequency and then you measure the energy of the electrons. But phi is from going from the Fermi level to vacuum. So phi is from EF to vacuum. And the electron affinity chi is from the conduction band minimum to vacuum. So you can think of it as the work done when an electron goes from the vacuum level to the conduction band minimum, or conversely how much energy you need to supply to take an electron from the conduction band minimum to the vacuum level. Let me just check if there are any more questions. Okay, so thank you. So again, there are no more questions. We will end the live session for now. So again, please do use the forum in order to post your questions, and then we'll be answering it. So we'll again be updating all the weekly materials, and if there is an interest from your side, we can always think of another live session sometime in April once we are done with all of the device part of the course. Alright, so thank you all for those of you who stopped by, and again, please use the forum to discuss further on the course.